The last topic that we've covered so far has been momentum, and that's the way that we observe and analyze objects that are interacting. These interactions might be collisions or explosions, so we're going to walk through the process of analyzing those. The first thing to do is to define the system. Is the system one object? Is it both objects? You should be able to make a sort of dotted line around the diagram or the picture that you've drawn and say, this is the system. The first question we ask is there a net external force acting on the system? If the answer is yes, then we can analyze that by means of an impulse. We say that there's some force acting, and the time span in which that force is acting gives us a change in momentum. And this follows from Newton's laws. We know that if there was no force acting, then there wouldn't be any change in momentum. So we can use this. The change in momentum, recall, is just an impulse. I use those two interchangeably. If there's no net external force acting on the system, then the total momentum is conserved. And we use this, which is extremely powerful in solving objects interacting problems. The initial momentum is equal to the final momentum, and if we have two objects at play, then we're going to add up both of their momentums before the collision and both of their momentums after the collision and set them equal to each other to solve for whatever the variable the problem is asking for us to solve. So we're going to look at 18 and 20. In 18, we have a tennis racket. And there's a ball that comes in, it hits the racket and comes off, and these angles are the same. The question is, what's the ball's change in momentum? And it's tempting to say that there isn't any change because this velocity is the same as that velocity, but there most certainly is. We have to analyze this in two dimensions. So before the collision, we have the velocity going this direction, and I broke that up into y component and an x component based on that angle. After the collision with the racket, the ball is now headed this way. The same angle is up here. We have a y component and an x component. Notice that the y momentum is the same. Both of these are going up. Both of them have the same magnitude, so we don't need to look at that because there's no change in momentum. But the x component does have some change. Before the collision, the x component momentum is going this way, and it has the value v cosine theta. Afterwards, it's still v cosine theta, but it's going that way. So I'm going to write an expression for the change in momentum just in the x direction, calling the left positive and the right negative. So the change in momentum is the final momentum minus the initial momentum in the x direction. My after case is m mass times v cosine theta, and it's going in the positive direction. Minus v mass times v cosine theta, but this is a negative component because it's going this way, which I defined to be negative. So we have two negatives that then become positive, making our change in momentum to mv cosine theta. On to 20. We've got two balls of the same mass. I just labeled them mass m because there wasn't any quantitative value given. We know that ball x has 10 meters per second of velocity going this way towards ball y, which is still. They hit each other and ball x goes off like this. We could assume that ball y is going to go off like that. We just need to do some momentum calculations in order to figure out the final velocity of ball y and the direction at which it goes off. So what I will do, and also I'll just show you this picture here before my calculations. This is ball y going off in this direction. We want to find that theta, and we want to find the overall velocity of ball y. We're going to use the x and y components, however. So let's look at the calculations in the x. Well, initial momentum equals final momentum. I have two balls, so I have two terms here. Mass times 10 going in the positive x direction. Mass times 0 because this ball is not moving. That's equal to the mass times the velocity of ball x, but that's only in the x direction, so I'm using cosine 53 to get the x component of this velocity vector. Plus the mass of ball y times the velocity in the x direction of this vector, so I'm looking at that here. Velocity in the x direction of ball y. The m's cancel out because it's in every term. My m times 0 doesn't matter, so I'm left with this expression. 10 equals 6 cosine 53 plus velocity x of ball y. So I can solve for that and get a velocity in the x direction of ball y of 6.4 meters per second. So that is 6.4 meters per second. Now I move over to the y in order to get the velocity of the ball y in the y direction. Initial momentum equals final momentum. This is the way that I start all of my momentum calculations if no net external forces acting. But in the y direction, there's no velocity. Ball x is moving, but it's entirely in the x, so there's no y velocity to start, so m times 0 and m times 0 are the initial momentum in the y. And I set that equal to mass times velocity of ball x in the y direction, which is 6 times sine of 53 plus the mass times velocity in the y, this component. I'm doing the same thing. I have to try and solve out that vy prime. The m's cancel out. This becomes 0 on the left side, so all I'm left with is 0 equals 6 times sine of 53 plus velocity in the y prime. That is what I'm solving for, and I get a value of 4.8. Notice that it's negative because, that makes sense. The ball is going down, and I've defined down to be negative and up to be positive. Once I get my two velocity values, velocity in the x, velocity in the y, I can solve for ball y's overall velocity and the direction it's going. So now we're over here. We're looking back at the triangle. We plug in these two values. We can use Pythagorean theorem to get this overall hypotenuse. Then we can use trig in order to solve for this angle. I'm writing out the expression tangent of theta is equal to opposite over adjacent, so 4.8 over 6.4 gives me 0.75, and I'm using the inverse tangent button on the calculator. Hopefully you've seen that before on your graphing calculator. It looks like this. You put in 0.75 and it gives you the angle. So this ball is going off at an angle of 36.9 degrees. That is problem 20. Hope this helps. Bye.